Hello and welcome to another lecture of ECE 205, and theoretically, unless something weird happens, our last week of ECE 205 that will be in an online format. So in today's lecture, we're going to undo everything we did in the last lecture by examining inverse Laplace transforms. Okay, so our goal is to be able to undo something that we've taken a Laplace transform of to figure out what that original function was. Okay, so ultimately we need to do these to be able to compute these inverse Laplace transforms, because if we want to do anything with the Laplace transform to maybe solve a differential equation, hint hint, then we're first going to do a Laplace transform, do some stuff, solve for something, and then we have to undo to get back into time space instead of S space. Okay, so our goal is to undo a Laplace transform, so let's just take a look at what that means. Well, really what we want to do is say, hey, if we're given some capital function f of s, and we know this f of s thing, and this is simply given by something that's of the form, the integral from 0 to infinity of e to our friend to the kernel, e to the negative st times f of t. So if we know this f of s, how can we find f of t? Okay, so that's what we want to do. So if I look at this and try to undo it, you might have a few options. One of them, like the first thought, might be, hey, I have this f of s is equal to this integral thing here. What if I say differentiate with respect to s, or maybe t, or something like that, to try to undo this integral, which here I should tell us that this is dt. Okay, so if I want to undo the integral, I have to differentiate with respect to time, and lo and behold, f goes away. Okay, that's not useful. I lose all information about f of s in that way. If I try to differentiate with respect to s or something like that, I can't actually undo the integral. Okay, so what are we going to do? Well, it turns out we have three options. Two options I'm just going to mention, but we're not actually going to do because it is well beyond the scope of this class. So the first option is to use complex analysis. Okay, what is complex analysis? Well, generally speaking, if you take a function that might not necessarily be a function of a real variable, but instead of a complex variable, complex analysis is basically calculus on those type of functions. So with this, we can get a thing called Mellon's inverse formula, and this formula gives me an analytic way or an exact mathematical function for what f of t would need to be. Okay, so in this case, we could say that the inverse Laplace transform, denoted by this guy here, this of my capital F sub s, what would this be equal to? Well, it's going to be equal to 1 over 2 pi. Okay, nothing weird yet. Okay, I'm also going to divide by I. Okay, that's kind of weird. Where's the imaginary unit coming from? F is real, right? And we're going to integrate from gamma up to gamma, but no, not quite gamma. We're going to subtract off I times t here. And over here, we're going to go up to a plus it. And I need to give myself a little bit more space because I forgot to drop the limit in. Okay, so now we add in the limits on the outside of this. Okay, so there's I limits and complex stuff all over the place involved, but the limit as t goes to infinity of this thing. And what is this thing the integral of? Well, just e to the st times f of capital F of s ds. Okay, so this e to the st bit might make sense because it kind of cancels out that in some sense if you multiply them. But here we have imaginary unit, we have limits, we have imaginary stuff going on here. And what's really happening is you're taking this function and embedding it in the complex plane. You're picking some real number here and you're integrating it from this point to this point along this curve and taking the limit as these go off to infinity. Okay, that's pretty exotic, especially since you haven't seen complex analysis. So let's not use this. Okay, since that's really nasty and beyond the scope of the class, now what? Well, the next option is equally ugly and actually kind of worse from a practical perspective, because while I could do this pretty easily, this other formula is just even more horrible. Okay, so what's this next one? Well, it's called Postinversion formula. Okay, so how does this thing work? Well, luckily, it doesn't involve any complex analysis, so it can't be that bad, right? Well, post-inversion formula, which again, we're not actually going to cover this in any detail. I just wanted you to know that these are things. But this tells me that the inverse Laplace transform of my f sub s, this thing is going to simply be given by this limit. Okay, so we still have limits as k goes to infinity. Okay, usually we don't talk about things that look like k, of -1 to the k. Okay, that alternates. That's not going to be good. Divided by k factorial. Okay, it decays. Maybe not horrible. Multiplied by this k divided by t. Okay, that blows up to infinity, but net this will keep it bounded to the k plus 1. Okay, this is fine. This term grows slower than that, so it's still finite for most nice functions. All multiplied by the kth derivative of the f function evaluated at k divided by t. Okay, so here this is a problem. Okay, if I give you an arbitrary expression, in particular something that doesn't behave particularly nicely, and ask you to compute the arbitrary derivative and take the limit as that derivative goes to the limit as the order of that derivative goes off to infinity, yeah, this is pretty hard to use in practice. And this only works in the case where my s of t function, this little thing that I'm trying to find here, is of exponential order. And it actually turns out that this extra little quantification here that we have isn't an issue, because if f isn't of exponential order, then I might be able to find its Laplace transform, but I'm not guaranteed to be able to find it. Depends on context, right? So I have to take that with a grain of salt. Okay, both of these options are bad. Both of these options are beyond the scope of the class. Number one is actually useful for a lot of cases because you can evaluate that using a thing called the residue theorem, and it's not too bad to actually evaluate that pretty quickly, to be honest. But computing this thing is just god-awful. So what can we do? Neither of these options are beyond, like, within the range of things that we could do for this class. So how could we go about and try to solve this? Well, really, what an inverse Laplace transform is doing is just undoing this thing here, okay? So if I have, say, a bunch of formulas that I took and I evaluated this kind of relatively simple integral here to compute the Laplace transforms of, then I could simply make a table of those formulas and kind of look at the thing that I want to try to find the inverse Laplace transform of and see if I can break it down into things that are in that table. Okay, so what we are going to do is use a table. Okay, so there's not really much introduction we really have to do. We can actually just start jumping into these and start computing some examples. So let's do that now. Okay, so let's look at this case here. Use a table of Laplace transforms to find these two things here. Okay, so rather than just saying, oh, here's the one I want to use, let's just take this and kind of split up my screen here and do a small practical demonstration for how to kind of read things off of a table in a slightly more efficient type of manner. Okay, so for this first one, I want something that looks like 1 divided by s squared minus 1. So basically, what I want to do, since I'm trying to find the inverse Laplace transform, I want to find something in this column here that matches the thing that I'm computing the inverse Laplace transform of. And once I find something that's a match, I then just kind of plug in whatever parameter I need to go to the other side. Okay, and do notice here we have a kind of a second page. So how do we just go about doing this? Well, let's just eyeball it. So this does not look like this, so I need a s squared. Well, here, if n is equal to 1, I have the s squared, but I have a minus 1. I can't really get rid of that, so that doesn't work. Here, I don't really have a gamma function thing going on. I don't really have s to the, so there's this one's not really going to work. Here, if this was s squared, I'd be good, so no luck there. Here, again, it can't be of this form, because if I expand this out, I'll never get a s squared minus 1 term. Here, this is closer. If I plug in, say, 1 for omega, it almost fits, just not quite, because I want this plus to be a minus. On the other hand, I have this other issue with this s up here, so that's kind of problematic. Okay, so if I go down to this one here, again, it doesn't really fit because I need the plus or the minus here instead of the plus, not quite there. So if I just keep going down here and keep looking at these, you can go which one of these looks right? Well, this again kind of looks close, but I have the S above it, and here we go. Now we're cooking on gas. So in this case, if I let b be equal to 1, then this is of the functional form of this thing here. Okay, so I do have to have a restriction on my S, but there wasn't any restriction mentioned here, which again is typical. You usually ignore the restrictions here. So what I can do is I can say, hey, if, for A, if it is the case that S is greater than the absolute value of 1, or just 1, right, then this Laplace transform, the inverse Laplace transform of this thing, will simply be equal to, well, this thing over here when I plug in 1 for B. So here this would just simply be equal to sinh of 1 times t, or sinh of t. Okay, so that's how to read these little tables, and in practice you can kind of ignore the domain here. Okay, let's look at the next one. So here I want s divided by s squared plus 9. So here this one kind of looks like it, but it's not quite there because I have a negative instead of a plus. But if we call up here when I had the cos, it was kind of exactly of that form. So here I need omega to be 9, or omega squared to be 9, so omega needs to be plus 3 or negative 3. And it doesn't really matter which one you pick because like Laplace transform isn't guaranteed to be unique. So here, and in particular, while I write this out, Laplace transform will not be unique because once you integrate things, you smooth everything out. But from here, if I compute this Laplace transform, I can, square that bracket, I can simply say that this thing would simply be cosine of 3 times t. Okay, so again, you could pick negative 3, you get the same results here. Okay, so yeah, that's pretty straightforward. When doing something, say in a assignment, if I ask you to compute a Laplace or inverse Laplace transform like this from a table, do mention like from the integral table we have blah, and thus if I let say omega be 9, then I get this. Something like that. So it's kind of clear what you're doing as opposed to just like, miraculously it popped up because I Googled the answer. Yeah, just make it clear that you know what you're doing and give justification there. Okay, so another nice thing that we might want to possibly have in order to compute these inverse Laplace transforms are some of the properties that we had in our last lecture for the Laplace transform itself, right? If I'm using tables, then it's nice if I maybe have some type of shifting thing I can do, or maybe linearity. And it turns out that you actually have both of those, but generally shifting is kind of more absorbed by the tables themselves. So let's just talk about this theorem 8.2.1 real quick. It's pretty straightforward, but just a little bit hard to prove with what we really have, namely the tables, but linearity property. So basically, if I have a linear combination of Laplace transforms, and I want to compute its inverse Laplace transform, then that's simply the inverse Laplace, or the linear combination of the inverse Laplace transforms of the Laplace transforms, right? This in words. If I have something like this, I could split it up. So if I gave you something like Laplace transform of this plus this, you'd split it up into these two cases and then figure out what those are, and you're done. Okay, so basically the classic proof that I'm used to using for this is basically going up here and first proving that this is a thing, and then since the integrals are linear, you could just split them up from there. But yeah, you could also do it here with doing the limiting factor here, but it's a little bit more complex because you have that k going into infinity, so yeah. But that's the basic idea. You don't need a proof for it, but there you go. So let's do another example here. So this example, again from the text, this 8.2.2, find the Laplace transform of this sum here. Okay, so if you're wanting to do something like this, you kind of have options on when you pull out constants and when you don't pull out constants. And generally speaking, what you want to do is first look at the Laplace transform to find the transforms that you might want to use. So here, just stealing from the text, they noted that from this Laplace transform table, we have these two little lines here, right? This 1 over s minus a and this omega divided by this thing here. Okay, so from here, if I can split these up to be of these two forms, then I can find the inverse Laplace transform. So let's just chase this out here with some fun background music. Okay, so for this first term, I'm just going to put this piece here in there. So if I look at it, this s minus a, well, if I just make a negative 5, then I could leave this as it is. And on the top, I want to have an 8. So I could pull out the 8 here and leave it like this. And if I want to be really precise here, I could take this minus 5 and rewrite it like. And there it's very obvious what I'm doing there. Okay, so now for the next term, I get. Okay, so if I compare these two kind of functional forms here, so from here, having this 3 tells me that my omega, to match the bottom, would need to be the square root of 3. So what I really want on the bottom is to rewrite this like. Okay, so here all I did was rearrange it from here. So if I'm using this formula here, that means I need to have a square root of 3 up here. So if I put a square root of 3 here, what's left? Well, I have a 7, and I need to pull out a divided by a square root of 3. Okay, so now I can use this information from the tables. So again, you could say from our Laplace tables we have this, thus this is this, and from here we just apply it, and we get. And there's our final answer, which we are nice human beings, so we box it in so the markers can see it very, very easy. Okay, so that's an example of using linearity, and again, looking up things at the tables to find what the transforms are. Okay, so now the rest of this lecture is purely to get you prepared for actually using Laplace transforms in applications. So let's look at a few examples that are very practical. You'll see why they're practical as we start actually doing things with differential equations. But what if I give you something more complex? So just stealing an example from the book, because again, good examples. Find this Laplace transform. Okay, so if you look at the tables, you'll see pretty immediately this ain't there, right? So we have some problems. We need to do some algebra to do something to make this work out somehow, okay? And a lot of this just kind of takes practice for figuring out how to break it down. So if at first this is difficult to try to figure out what to do, don't feel bad. Just pay attention to the examples here, do some practice problems, and ask questions like, how could I turn this one out to make it work, okay? And here, just as a thing, you don't need to memorize the Laplace table. I will give you the various transforms that you will need if Laplace transforms are on any particular test, okay? And they will be tested on, of course. But yeah, you'll have the Laplace transforms you need there. Okay, so now instead of just telling you, hey, yeah, let's use this, it works, let's explore how to figure out which one to pick, okay? Because that's a skill you will need to develop. Okay, so if I look here at something like this, there's kind of two natural things that should scream to mind. One, you should start thinking, hey, I could do partial fractions. And if I do a partial fraction decomposition on this, if I can factor the bottom nicely, then I could split it into two sums that would be of the form something, so some function here, over something that looks like s minus a, plus or minus some other thing over here, s, say, minus b. Okay, so if I have something of this form, then we know that we have these nice Laplace transforms, this e to the at. And we might have to do something fancy at the top, so I might need to do something like a cosine or a sine, depending on what's happening there. But yeah, so it's feasible to get things to work out like that. That said, while partial fractions do work well, there's other methods that can work well within certain contexts. And by work well, I mean save you the algebra of having to do partial fraction decomposition. Okay, so if I kind of look at these things here, I have a thing here, this these terms here, that are kind of similar to the form of this thing that I have here, right? So like this one has s minus lambda, well here I have 3s minus 8, that could be a match. Here I have a s, here I have a b, well if I split this up into two fractions, I could get matches there. that type of a thing. So our intuition just from here could be screaming, let's try one of these. Okay, so here you kind of say, hey, this bottom really isn't of the form s minus something squared. So these bottom two are kind of out just from that, okay? But you could also argue, hey, this really isn't of this form, but we have a trick up our sleeves that hopefully you remember, but if you don't, it's not necessarily bad here. Okay, what we can do is we can do a thing called completing the square. So what we can do is simply note that this s squared plus 2s, well, this term here, if I just focus on it, if that 5 was instead a 1, I could factor this into s plus 1 times s plus 1. So what I can do is I can add a 1, and then I could subtract a 1 here. Okay? So if I do this, something nice and miraculous happens, namely, I get to complete the square. If you don't recall this thing, it's kind of the way you prove quadratic formula. So it's kind of useful to go back and maybe look at a proof of the quadratic formula if you haven't seen that. But nevertheless, this whole thing can now be simplified to this term here. Okay, and just again, that's called completing the square. Okay, so after I complete the square, and I'll zoom out here a bit, there, I think that'll make the view a little bit better. So after I do this, I can now say, hey, this Laplace transform that I had from over here, this thing, can now be simplified as follows. Okay, so you could do this in line here with this extra thing, but I just wanted to put that completing the square as a second step, just in case you haven't seen that for a bit. But basically, you always add and subtract whatever this thing is divided by 2. Okay, so now that I have something of this form, I want to go look at the tables and see what we can do with it. Well, I do have an s term here, so I have this 3s. And here my lambda needs to be minus 1, right? Just because I have this plus 1 here. And my omega needs to be 2. Okay, so from here, let's just try to get this cosine bit as much as we can. Okay, well, to get this cosine bit, I really need to get a single s sitting here. So let's split this up into 2 little bits. Okay, so here's how I'm going to do this. Okay, so why did I do the split? Well, there's lots of options. You could think a priori, hey, I just need an s minus the lambda term here. So in this case, that'd be s plus 1 because lambda is negative 1. But then you'd be left with a 2s over here, and that's not directly the cosine bit, so or the sine bit, so you'd have to go back to the drawing board to clean it up a little bit. But here, I now have a clean single number here that I could pull out whatever scalar I wanted to simplify this however I want. So this actually gives me progress towards getting a solution. So now what I can notice is for this first one here, if I just look here, what do we have going on? So here, if we let lambda be equal to negative 1, and if I let my omega be equal to 2, then here, this is exactly of this form with an extra factor of 3. Okay, so I could use the linearity of the inverse Laplace transform to pull out the 3, and I'm good there. Now over here, if I want to try to turn this into this sine thing, what I need to notice is that my lambda, again, is just equal to minus 1. My omega is 2. So if I want this to work, I need to turn the 5 into a 2, and again, I can use the linearity property to do that. Okay, so just removing that here and putting back the inverse. So doing this, I get okay, and again, recognizing how to break this down is a skill that you'll have to develop from kind of seeing some examples, but this is one of the very common ways to try to think of how to break it down. Okay, so that kind of ties back into the thing I said in ECE 108. Math has a lot of creativity involved in it. Here, you have creativity on how to use this table to make things work. Okay, so from here, I can now simply apply the data from the table. So here I'll put a table. Okay, so from here, if I take this thing here, this would simply give me a e to the negative t times a cosine of 2t. And on the other side, I have my 5/2. So here, my omega was 2 and my lambda is -1, so I simply get this term here. And of course, I can simplify this if I want. Okay, isn't that so much easier than learning complex analysis just to do these intervals? Okay, so that's one example there. Let's look at some more examples now. Okay, let's look at another one of these computing the Laplace transforms of a rational expression like what we just did. Okay, so again, the reason why we're focusing on these, as you'll see in the next lecture, these type of functional forms appear all the time when applying this Laplace transforms to try to solve differential equations. Okay, so what do we do here? So we have options. We could do the completing the square thing. So let's just try this first to see why this isn't going to be the most optimal thing to try. Okay, so if I wanted to do the completing the square, so CTS for it. So if I wanted to do this, I would want to simplify this expression here. Okay, so the way that I would do this is I would add and subtract this factor divided by 2 quantities squared there. So from here, I would simply get this. Okay, so after all the smoke clears, this term would simply factor into. Okay, so here this is just kind of the completing the square standard trick. Yeah, so since this thing's a negative, you get a negative here, and if you multiply this out, if you square this, you get the term over here, and if you add it to itself, you get the 3, and yeah. So from here, this would give me that my expression that I'd need to simplify would be. Okay, so that's kind of a doozy. There's fractions involved. It's not the cleanest thing sitting here, but it's not too dissimilar from the case that we just examined, right? But here, if I wanted to have one of these exponential terms like this, my lambda would be 1.5, so I'd have to kind of work around that. Could be a bit annoying. Here, I have a minus instead of a plus, which kind of throws out these options up here. So you can go forward with doing this, but there in fact is a better way for this case. And mostly the main issue here is this -1/4 is just bad to deal with, really. You kind of are stuck with the differing signs here. Okay, so that as an attempt aside, let's throw this away, and instead of doing this, we'll notice the thing with partial fractions that I mentioned earlier, kind of hand waved about how that would work, but let's do partial fractions and try to work this out. Okay, so here we're going to try partial fraction decomposition. And before you ask, yes, I could have done that up here, but I just wanted to show there's different ways of going about it. Okay, so since we want to do a little bit of math here, let's make our screen a little bit bigger to enjoy the extra screen space. Okay, so from here, if I want to do partial fraction decomposition, here I first have to note how this thing factors. Well, pretty clearly. Okay, so now from your days of doing partial fraction decomposition in the past, you should recall that the ansatz that we'd want to make is some constant divided by this plus some constant divided by this. Okay, so if I chase this out, we get. Okay, so now my goal is to solve for A and B. So now I really have kind of 2 main methods and 1 little sub-method. So let's just go through all of these. Okay, so method 1, what I can do is in order to solve this, I could simply multiply by this term here to get an algebraic equation. So if I do this, I get this thing here. So now I have options. So these are just polynomials in terms of S, right? So what I'll call version 1 of going forward from here, what I could simply do is set up this as a system of equations by expanding out the left or the right hand side and setting the coefficients equal. So if we do this, So now what we would do at this point is solve this for a and b. Okay, so I'm not going to chase out the details, but here we get these two solutions here. Okay, and there, solving it, that's where you would do some linear algebra stuff. Okay, so that's method 1, version 1. What about version 2? So this is a little bit improved, but still not the best. The best method, generally speaking, will be method 2. So what can we do over here? So instead of solving this by doing it this way, we can note that, hey, we want this to be true for every value of s, but if I'm going to find these values of a and b that work for all values of s, then they would have to work for particular values of s. So instead of trying to deal with it with arbitrary s, we can start just by picking, say, a couple values of s to get simpler equations. Okay, so how should I pick these? Well, if s is chosen to be 1, nice things happen. What do I mean by nice things? This goes away. So if I chase this out, so from here you immediately get that a is 5. And further, now if I pick s to be 2, this cancels and I see that. So I have method 1 where I multiply everything out and go forward from here. Okay, so now there's method 2, which actually is a named method known as Heaviside's method. So what can we do here? Well, if I want to save myself a little bit of work of actually writing out this equation, I could really just do the step of writing it out like this and plugging in the numbers at the same time. Okay, so basically, if I wanted to isolate for the a, I would ultimately want to plug in s is equal to 1 after multiplying everything out. So simply what I do, at least mentally, is I ignore the terms that have a s minus 1, namely this s minus 1 here, and the factor of s minus 1 that would be over here, and I ignore all of the other factors over here. Okay, so from here, if I plug in 1, I would simply say that, hey, my 3 times 1 plus 2, all divided by the remaining term here, in that case it would be a 1 minus 2. This thing would simply be equal to a. Okay? So from here, this gets me the same result that I had here, a is 5. And for the second bit, I would simply say, hey, if x is 2, I could do the whole multiplication thing, but instead, I just ignore the factor of s minus 2 over here, and I can simply say b is equal to 3 times 2 plus 2, all divided by, well, when I remove the s minus 2, I'm left with a s minus 1 term, so 2 minus 1. And that's the exact same thing that I had before. Okay? So you can choose between these two methods. If you're uncomfortable with this when you kind of first start out, it's really just a shortcut. So if you don't feel comfortable doing the mental math, making sure everything checks out, then definitely do it kind of the longer way by writing it out first. But it's up to you which one you choose to use. I generally prefer this method if I've been doing a lot of these for like kind of maybe a shortish period of time. But after, like if it's been months since I've done a partial fraction decomposition, generally I'll write this out just because I'm not in the habit of using it. But your discretion is there, so you have your choice. Okay, so we have actually gone through in these 3 different ways to actually compute what this thing is. So if I zoom out here, so now what we can say, no matter which one of these methods we picked, is that a is definitely minus 5. So we can say this is equal to minus 5 over s minus 1, and b is definitely 8, so I get this term. Okay, so this is how that thing breaks down. Okay, so now my goal from doing all of this stuff was to find an inverse Laplace transform. Okay, these are of the forms of those exponentials. So if I just kind of break it out for a second, each one of these is of this form here, right? It's 1 over s minus something. So this one will be e to the minus t times negative 5, and this one will be 8 times e to the minus 2t. So let's just chase this out using my tables from here. Okay, so cue the music. so that was pretty straightforward after we chased this out. Okay, and in general, we're going to examine a lot more functions of this form and compute lots of inverse Laplace transforms. Okay, so get used to and get some practice in with partial fractions again if it's been a while. Okay, so let's look at another example now. Okay, so I skipped example 8.2.5. You can do that one on your own. It's just kind of rehashing what we did before. But let's look at this one. So here our partial fraction decomposition needs to be a little bit more fancy because we have this term squared. So if you don't recall from calc, the functional form for this partial fraction would be this term here. So why do I need to bring in these extra terms here? I don't want to get into the details. You should have seen them in calc. If not, we can kind of go over it in office hours type thing. But basically, if you have something here to the power of n, you have to add these extra repeated terms here. It's kind of similar to the rules where you multiply by x in those particular d's. Okay, so if I wanted to try to solve this, it turns out that Heaviside method doesn't work to get us all of the details. That's kind of unfortunate. And the reason why the method fails is when I plug in -2, kind of weird things happen here. But we can glean some information here. So if I were to expand this out by multiplying by this s minus 1 times s minus 2 quantity squared and kind of rewrite it out in the long form, we get okay, so now we have some options, but in general, our goal is just to solve this. So the book gives one method where you kind of expand things out. Actually, I lied. The book does what I was going to do anyways. So let's just do what the book does because that's what I was going to do. So basically what we want to do is pick values of s such that we can get some of these terms to cancel to solve for a, b, and c. Okay, so if I want to solve for a, I could simply note, hey, if s is equal to -1, it cancels out this term and this term. So writing this out explicitly, we get this expression here. Okay, so -1 plus 2 squared, that's just 1. So immediately from here, if I simplify this expression over here, we can solve this for a, right? So here, after the algebra clears, we simply get that a is just 2. Okay, so now I know what a is, so I don't actually have to worry about canceling out this term, just to be a little bit exact here, because even if it doesn't cancel out, it has a numeric value. I can plug in 2 for a. So now let's just kind of focus on c. Why c? Well, b has both of these terms, so I actually won't be able to cancel out b entirely, so it's just convenient if I get c first. So to get c, I want to cancel out the a and the b terms, so let's let s be -2. Okay, so if I plug in -2 in for here, this is what I get. And I just get this here. Okay, so here I just drew a line just because I really don't care what this number is here. I mean, it's going to be -4 times, or sorry, 4 times -2 plus 10, but this thing here was 0, so it doesn't matter what it is in the end. So from here, if I chase this out, I get 8 is equal to -c. So from here, I simply get that c has to be equal to -8. Okay, so now that I have a and c, I can pick some random value to get b. Okay, so from here, it does not matter what we pick, but it's pretty convenient to pick 0, right? Because if it's 0, everything kind of cancels out and things are a bit nice. It could also be nice to pick, say, -10/4 to cancel out that term. It's really your choice, so kind of pick your own poison here, so to speak. So doing this gives and then finally, just plugging in the values for a and b, we get okay, so from here you just chase out the algebra, and I'm skipping over a lot of the algebra arithmetic steps because you should be able to do arithmetic, and it saves a bit of time on the lectures, which I know are quite long for you guys. They're long for me to make, so it's definitely long for you. But here we get these coefficients from here. Okay, so you should have seen this technique before. If not, you've now seen it. This is how to approach these type of problems where I have a repeated root, where it's repeated twice. Okay, so if I put all this together, I can simply say from here that the inverse Laplace transform of f would simply be this term here. And again, I'm getting this just by plugging in 2, -8, and -6, right? Okay, so perfect. Now that we have this, we can now actually, sorry about that, I need this symbol here. Sorry about that. Be very careful with things like that. It's easy to make mistakes. So from here, we know all these are going to be exponentials, so let's just chase out the details with a little bit of music. Okay, so what is the Laplace transform of 1 over s plus 2 squared? How do I find this one? Well, this basically, if you don't have it memorized, go back to the table and let's check this out from here. Okay, so it's clearly not e to the at, but I have this nice nifty-difty little formula over here that allows me to get higher powers of the polynomial in the bottom. So from here, if n is equal to 1, then 1 factorial is 1, and I get s minus a squared. So from here in the table, I simply get that this would simply be t squared times e to the 2t. So from here, and here I lied, be careful with negative signs. You want a negative on all of these guys. So definitely check your work for little negative signs, things like that. There we go. I'll leave that oopsie in there just so you can see that everyone makes oopsies. Okay, so from here, again, just t to the first because I want a 1 here, not a 2. Okay, so this is my Laplace transform here. Okay, so it's kind of a combination of using the tables and partial fractions. And quite honestly, partial fractions will take you a long distance with doing linear transform type or Laplace transform type things. So definitely it's the main toolbox or kit in your toolbox that you're going to have. Okay, let's look at another example. Okay, so to save time, I'm not going to do all the Laplace transform stuff here, but instead I'm just going to focus on the partial fraction decomposition with the assumption that you haven't, like some of this might not be familiar, but basically the way these problems go is you do a partial fraction decomposition, and then after you do that, you look at the tables to figure out what exponential type terms you need. Okay, so how would we do the partial decomposition of this thing? Well, here we make this ansatz. Why this ansatz? Because it works. Okay, there is some rhyme and reason to why you pick these, of course, like with everything in math. But basically, if you have a root that's repeated n times, you're going to keep repeating this with higher factors. So let's go through and play the chase the detail out game. So here, again, our Heaviside's method's not going to work particularly well, so let's expand everything out. So doing this, gives me this thing here. Okay, so from here, I want to guess values to get my solutions for A, B, and C. Now, do note in your book, they notice that you could simplify this term here out, but that's not immediately obvious, so I want to give you an alternative method that's more obvious, in my opinion. Okay, so the first thing we can do is, very quickly, we can figure out what C is. So if S is equal to -2, what happens? Well, in this case, we simply get... And immediately, if you chase this out, we find that C is just going to simply be equal to 21. Okay, so now we want to find B. Well, this can be a bit of a pain, right? Because A and B both disappear at the same time if I pick values for S. So what I'm really stuck with here is picking two different values for s and hoping things work out nicely. So here there's one easy way to try to get a solution from here, and that's to pick these two values for s. So here I could pick one where this becomes a 1, and then I could pick one where this becomes a negative 1. And it turns out that that'll be useful here. So the values that I want to pick in particular would be -3, and s is -2. Okay, so I'm going to do both of these at the same time. So doing this gives me okay, so now from here, this term here, this -1 squared, will just give me a 1a. So I could simply add these equations together to get a single equation for a, solve it, and then get an equation for b from there and solve it. So I'm not going to do those details here, but okay, future math here, I pushed the wrong button, but adding them gives a is equal to 1, and then from there, if I plug that into any of these equations, you can solve it for b forward. Okay, so if I put all this together, I simply plug my coefficients a, b, and c in, and I get my f is given by this. So let's look at another example. So this, again, is an example taken from the text, other than we're stopping at computing the partial fraction decomposition, just because I think that's the main thing students will struggle with here. Okay, so how do I find the partial fraction decomposition of something that looks like this? Well, there's kind of two things going wrong here, so to speak. So here I have this s times this kind of complex thing here, and then I have this decently complex numerator with a s squared sitting there. So if I tried to look for partial fraction decomposition in the standard way, I can't really factor the thing in the brackets. So the default guess would be that f of s was just given by some constant divided by s plus some constant divided by the other term. But there's a problem here. Since this thing is quantity squared, in the partial fraction decomposition, if I try this, it will actually fail. So the proper ansatz in this case, since this is a quadratic polynomial, is to assume that this top is the form bs plus c. Okay, so I could do partial fractions of this form and everything will work out here, but if I do it without having that bs term, if I just left it as a b, this would fail. Okay, so now I could just blindly do partial fractions looking for something of this form, but it's useful to notice the only reason why I'm really doing partial fraction decomposition in the first place is to actually get these inverse Laplace transforms, right? So let's see if I have anything of this form sitting in the table. I know I have a over s, right? That's 1 over s. But do I have something that looks like bs plus c over something of this form? Well, if I recall earlier, the shifting principle gave me, in order to get something of the form here, I really had these two sine and cosine things sitting here. Neither of these terms look of this form. Okay, so I could do something like this and then do the manipulations that I did in the first problem, but if I think cleverly, I could automatically try to look for something that's already kind of in the sum of these two forms. Okay, so if I just look at this for a second, pull this over here, there we go. So if I just look at this for a second, I really want something that looks like s minus lambda plus this omega. Okay, so here I could have some scalar multiplied by this, and that would be fine. But if I could get something that looks like this in my partial fraction decomposition right off the bat, then I'm good because I have to do less manipulations later, right? I can avoid basically rehashing that first example I looked at. So what we can do here is, instead of assuming that it's bs plus c, which is kind of the standard assumption there, I can assume the same thing, but in kind of a fancy way, okay? So b, I want this to be s minus lambda, right? So lambda would be the term here, or negative of this term here. So I want this to be s plus 1. And then I want some arbitrary constant c, which ultimately will be my omega. Okay, so if I can solve this thing of this form, then the next step after, oops, I need a plus here, the next step after I do my partial fraction decomposition would simply be to split this term here up. And once I split this term up, I have my terms that I need for my inverse Laplace transform. Okay, so let's basically hash through the stuff here. I'm not going to explain any of the details because it's the same thing where you pick values of s and try to solve it. So just long montage music time. Okay, so fair bit of work here, but let's just briefly discuss why I picked these values that I picked. Okay, so if I zoom out, if I look at these equations here, so if I plug s is equal to 0, this term in front of here goes away, and I can solve for a immediately. So that's why I picked it. So next up, my goal was really to try to isolate either b or c. So here the only way I can isolate b from c in any way is to pick s to be -1. So if I pick this, it lets me get rid of the b term, and I'm still left with the a and the c, but I already know what a is. So if I do that, I can just do Gauss back substitution here to get the solution from there. And finally, for the last point, it doesn't really matter what number you pick. Just pick something where the algebra isn't god-awful, and usually picking a number where things turn out to be decently small works, right? I can't pick any number other than the two I've already picked. So 1's a good number, so I picked 1. Okay, so after I chased that out, I found what b was, and then putting all of that together, I simply get this partial fraction decomposition here. Okay, so if you want to see the details for the final answer, it's in the text, but basically we know the Laplace transform of this will be 1/2 e to the x, or sorry, just 1/2 in this case, sorry about that. And then here we would split this into the bit in kind of this underlined color here, and that one will give us a cosine term, and then this bit here will give us a sine term, and that's just coming from these bits over here. Okay, so that's how that one works. Again, the hard part is figuring out how to do the partial fraction decomposition and then actually going through and doing the partial fraction decomposition. Okay, let's end with one final example, and I will also speed through it, and we'll just focus on the hard bits. Going over all the algebra you should be able to do on your own pretty quickly without watching me go through the algebra. Okay, so how should we choose to partial fraction decomposition this guy? Well, s squared plus 1, that does not factor. S squared plus 4, that does not factor, right? To factor it, I need to go to complex numbers. So I'm stuck with both of these terms as is. So here, my default thought would be that this f of s should go to something of some functional form divided by s squared plus 1 plus another functional form over s squared plus 4. Now again, since these are quadratics, I have to guess that this will be of the form ax plus b. Okay? And over here, I have to guess that this will be of the form cx plus d. Okay? Those are the forms that I'm stuck with because it's a quadratic. If it was a cubic, I would need a quadratic at the top. Okay? So from here, I could just go straight forward and chase this out, but it turns out that there's a nicer way to go forward. So you might be thinking when I say there's a nicer way that we should go back over to our friend Mr. Tables and see if there's a nicer functional form that we could possibly get out of here to try to find something there. But no, I mean something differently entirely. Okay, so here, just TLDR, just kind of look at this. Here we know we're going to be of this form here for sines and cosines, since I have something like s squared blah da 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 plus this. So I'm really going to do things with lambda is equal to 0, for both of these type cases and split them into sines and cosines. So what do I mean by I can do something easier here? So this is a trick that sometimes is useful. Oftentimes you don't run into it often enough to recall this trick. But what you can do in this case is reduce the power of these s terms by doing a substitution. Okay, so what substitution is it that we're going to make? And here I noticed a typo. This should be s, not x. Well, if x is equal to s squared, then the denominators here simplify to x, and they could maybe think like, oh, I'm stuck with that square root of x on the top, but actually that's not a problem here. So what I can simply do is I can think of, hey, I have this possible transform, and instead of doing partial fraction decomposition of this function, I can first look at the partial fraction decomposition of this function here. Okay, so this is very similar to this one here. I just need to multiply it by 8 plus 3s and then do my substitution. So here, this partial fraction decomposition we know needs to be of the form and here we can use the Heaviside function or Heaviside method to make this thing work out to be able to find a and b. So we can do this really quickly. So what we're going to do is do the partial fraction decomposition here first, and then notice that we can multiply it by 8 plus 3s, and then do the substitution, and we're good to go. So let's clean this up and then do that. Okay, so they're kind of just cleaning it up here. We need this, but that's a lot of work. You can do it. It's up to you. But here it just so happens that we can do a reduction of order by picking this thing here. And then if we find this partial fraction decomposition, we can then construct the other one. Okay, so from here, using our Heaviside method, we would simply say a is equal to, well, if I plug in -1 and ignore those terms, over here I would simply have my 1 over, in this case, -1 plus 4. Okay, so here if I simplify this out, that tells me that a has to be equal to 1/3. Pretty trivial. Okay, on the other hand, I would get b, if I plug in -4, I would simply get this term where I ignore the plus 4 terms, okay? So from here, this is just -1/3. Okay, that was fast. That was a lot faster than solving the long way here. Okay, so now that I have this, we could say so. Okay, so that's pretty simple. And now I don't want the partial, I didn't want to simplify this. I wanted to simplify this term. So I just multiply by that 8 minus 3, or plus 3s. So from here, put... Okay, and that is our partial fraction decomposition. Okay, so if you want to do the last steps to finish the problem, all you would have to do is look at the questions for a little bit and see, oh, here's how I can factor out the terms to split each one of these terms into sines and cosine terms here. Okay, pretty straightforward. Hopefully you don't have a hard time with this. Hopefully it's kind of a little bit of an easier lecture. Okay, so for the assigned reading, I want you to go through section 8.2. We basically mirrored everything that they did, other than I didn't do the final steps for doing Laplace transform stuff. So it might be good to practice those on your own, like try try to finish the question and find the inverse Laplace transform of this on your own. Check with the book, that type of thing. For your practice problems we have here, and for your memes, this is what we have. Okay, so you don't realize some of this stuff yet, but you are the sleeping people here, and Laplace transforms actually are going to save you from having to do a lot of hard things with second-order differential equations. A lot of the things that we've done already can be addressed by doing Laplace transforms. Not all of them. Sometimes you can't do it with the Laplace transform, but you can with variation of parameters, undetermined coefficients, that type of thing. Sometimes it's easier one way versus the other, but generally speaking, Laplace transforms will help you solve a lot of second-order differential equations. And in order to actually do that, you need to find the inverse Laplace transform. Now, you haven't really seen the monster in all its detail because we didn't cover how to evaluate these integrals, but these expressions look really bad, right? This one is really bad. This one's not too bad, given that you can do things with Jordan's lemma and hopefully the residues work out well for residue theorem. But this isn't the cleanest looking thing, right? So what's really saving you from having to do that is partial fractions. So think partial fractions. It's a good cat, and I hope you enjoy your day.